Good afternoon, everybody.
Good afternoon.
Hello.
Hi.
Is it just my computer or is everybody's computer moving extraordinarily slow?
Mine's perfectly fine.
Yeah, well, so is your bedroom. You have like a perfect bedroom back there. But you don't care. You have way too much discipline.
Good.
Dr. Musgrave,
Yes.
can I ask you a question?
You just did.
You know all this, the Vesper stuff?
I'm sorry, what's that?
All the Vesper stuff?
Yeah.
Is that on the test?
No.
It's just extra credit?
Yes.
Can you get through this class without understanding all of it?
Yeah, I think so.
Okay, just wondering.
But, you know, it doesn't hurt.
Well, I went through all the videos and everything and tried to take some of the quizzes, but I didn't do very well. So I clearly am not getting it well enough to be tested on it. And I can watch them again, but I was just wondering how important it was.
Well, not to your testing, no, not at all.
Okay, but it helps. I get that.
I think so. Okay. Chat box is so big. Good Lord. Ah. All right. I'm going to rely on you guys to tell me when somebody's in the chat box and they need something. All right. We'll get started. 12:30. We're going to be working through acidity today and figuring out our two compounds, which one is more acidic. So first of all, let's look at some definitions. An acid is a compound that produces H+ in water. Would you please mute? Please. Thank you. Bases produce OH- when dissolved in water. If you've got two compounds, the more acidic compound will be the one that produces more H+, which I think makes sense. And here's the important one. The compound that produces a more stable anion will produce more H+. Okay, so here's what we've got. This is a situation. If you've got an acid, that I'm calling AH, that produces an anion, an H+, and we've got another acid, that I'm calling BH, that produces B- and H+. So the more acidic compound out of these two, out of AH and BH, will be the one that produces the greater amount of H+. Does anybody have any questions about that? So the other thing that follows from that is that if AH was producing more H+ than BH, it would also mean that it was producing more A-. And the reason it would produce more A- is because A- is more stable than B-. So A- is more stable than B-. Could be the other way around too, but means AH is more acidic than BH.
So you'll know if more H+ is produced depending on the like the front number, the super.
Well, it's not so much a front number. It's based on the stability of the anion. I'm going to show you how to look at two compounds and determine which one has the more stable anion. That's what we're going to focus on, Sierra.
So it's not a case of how many hydrogens are in the molecule.
Nope, it isn't. Not at all. Not at all. It's all about how stable the anion is, that negatively charged compound, how stable it is. And I'm going to show you how we determine that. That's going to be the focus of what we're doing today. Okay, so here I'm going to go through 4 different scenarios here. 4 different scenarios. And the first one here is comparing these two compounds, NH3 and CH4. I'm not going to rewrite the equations over here, but you can see what happens is that they're each going to produce H+. Now, the reason we know that is because we're asking which one is more acidic. By definition, acidic compounds produce H+. So if we get H+, it means we also get a negatively charged species as well. I go into more of an explanation in the video, but I'm not going to go into it here. But I will say that in order to maintain electrical neutrality, if this is positive, then this has to be negative over here. So the bottom line is we've got NH2- and CH3- along with H+. so far. So anytime we split up any compound, we take off the H as H plus, and then the negative charge ends up on the atom that the H was originally attached to, which I think makes sense. In this case, it's the N. In this case, it's the C. So NH2 minus, it's going to be the N that carries the negative charge because that's what a hydrogen was attached to. In the case of CH4, it's going to be on the C because that's what the hydrogen was originally attached to as well. In this scenario, when we're trying to determine which anion is more stable, we look at the electronegativity of the two elements. In the case of NH2 minus, the N is on the N has a negative charge. In the case of CH3 minus, the C has a negative charge. Now, N is more electronegative than C. Therefore, we know that NH2 minus is more stable than CH3 minus. Now, going back to electronegativities.
Does that also have to do with affinity for bonding?
It's more about electronegativity, because what happens is that if an element is more electronegative than another element, it draws that negative charge in closer to the nucleus, which stabilizes it more. The nucleus is all positively charged, if you remember. Let me see, I'm just trying to look for my Paulings. Okay, here we go. So the electronegativities, if you remember, fluorine is the most electronegative. So whatever's closest to fluorine out of two elements will always be more electronegative. So in the case of C and N, you can see that C and N here, N is more electronegative because it's closer to F in this diagram. But I just try and look at the fluorine, whatever's closest to fluorine, that's what I go with. It's really just between these, generally speaking. Okay.
So, excuse me, so nitrogen, it's going to want to keep its electrons more, which means it's going to want to bond with the hydrogens more than carbon would, right?
Oh, I don't know if I'd say that. I would only say that the N draws the negative charge, the minus on it, in closer to the nucleus. That's all I would say. And the C does, because it's more electronegative. Is that okay?
Yeah, that's right.
Okay. So once we know which anion is more stable and it turns out to be this NH2 minus, then what I would say is that since NH2 minus is more stable than the CH3 minus, the other anion, we know that NH3, this compound, is more acidic than CH4. So because one anion is more stable than the other, this compound here is more acidic than this compound. And that's the kind of, this is how I'm expecting you to lay out your answers. Because you'll be asked to draw out the reaction, just like I've done here, figure out which anion is more stable, and then write that statement that links anion stability to acidity of the original compound. Now, the other thing I want you to understand here is that NH2 minus is not acidic. I'll say that again. NH2 minus, CH3 minus, the anions, they're not acidic. Acidic means willing to produce H+. If something's already negatively charged, it's not going to produce H+. Or generally speaking, it won't, or it's more difficult to do so. So what I'm talking about here is just what happens when the NH3 splits apart, forms NH2 minus. The NH3 is acidic. The NH2 minus is not acidic. That's where people kind of get mixed up here with the statement. They'll say NH2 minus is more acidic than CH3 minus, which is not a true statement.
Professor, I have a question.
Mm-hmm.
So is it not true that the NH2 minus could not dissociate into NH minus 2?
It's unlikely, because once it's already got one negative charge, getting that second negative charge is even more difficult.
Okay, so we only look with like one dissociation.
We are, yes. Yeah, but there are plenty of elements, or sorry, plenty of compounds out there that do more than one dissociation. We're not looking into any of those, though.
That would be in the presence of another compound that fights for the hydrogens more,
Well,
right?
It's possible, but there are also compounds that have stable negatively 2 or negatively 3 charged anions. It's possible. not dealing with any of them here. All right, so this instance, I'm going to do a little summary over here. This is the first scenario, scenario 1. Scenario 1, we have the anions, which are going to be, I'm going to call them Rx minus, Ry minus, where I'll say X more electronegative than Y. All right, so that's our first scenario. And whichever one has the more electronegative atom with the negative charge, that is going to be the more stable. That's going to be the more stable anion. Does anybody have any questions so far? All right, scenario 2. So we're dealing with line structures here. And if you look at the two compounds we're trying to compare the acidity of, they're up the top here, these guys here. It's pretty easy to see the difference between them. Look where the F's are. In one, the F is over here. In one, the F is over here. It's further away. So you're looking at this, and you know that there are plenty of hydrogens on these carbon atoms here. These points are all carbon atoms, if you remember from last time. But the most acidic hydrogen in the compound is going to be the one that's attached to the oxygen. And it's the only one that's drawn in, but that's not the reason we choose it. We choose it because it's attached to O, and all these other ones are attached to C. And what we just talked about was O being more electronegative than C, so it's much more likely we lose a hydrogen off the oxygen than we do the carbon atoms. So when we're looking at the pattern here, it's pretty simple. The H plus comes off, and we leave a negative charge on the oxygen. That's it. That's all we do. So now we have to figure out of these two anions that we formed here, which one is going to be more stable. And this is going to be determined by bond polarity. And we talked about this the other day. And what I'm going to do is I'm going to draw the A minus here, and I'm going to draw it, I'll draw it as a line structure first. And then what I'm going to do is I'm just going to focus in on what we're seeing here. So just a sort of like an inset, if you will. So that's what we're looking at. It's actually just a CF bond. If you remember what we talked about the other day when we were talking about bond polarities, what we know is that if we put partial charges on here, we put delta minus and we can put a delta plus on that C. So what does that mean? It means that when we put those delta pluses and delta minuses on here, we can see that in this instance, the delta plus is going to be closer to the O negative, and here the delta plus is further away. So what we know is when we're dealing with opposite charges, that's a good thing. They attract each other, they stabilize each other. With like charges, they repel each other, they destabilize each other. And that's what we're looking at here is the case of attraction, because the delta plus can stabilize the O minus. But I think it makes sense that the closer the delta plus is to the O minus, the more it can stabilize it. That's what makes A minus more stable.
I'm sorry, I think I missed it, but why did you put the partial charges on the fluorine and carbon?
Because fluorine is more electronegative than carbon, so the electrons in the bond will be closer to the F than they are to the C. In the case of the CHs though, they're practically non-polar. So we don't talk about polarity of CH bonds. Only the CF bonds.
All right, that makes sense. Is that something you're going to want us to have written out when we're doing these, all the partial charges
Yes.
for things.
Yes.
Then would we also be writing it for the double bonded oxygen?
No. And the reason is because it's the same in both. So it's not the reason for the difference in stability. The reason is the location of the CF in each instance. So
Okay,
that's the
we're
only,
writing in because it's significant for this
Right.
example.
That's
Okay,
correct.
thank you.
Yeah, would there be a delta plus and delta minus on here and here? Yeah, absolutely there would. But what's the point in putting it on if it's not going to make a difference to anything?
Can you repeat what you said about the delta plus and the delta minus? Something about whichever one's closest to the O. What were you saying?
Well, the O minus. Look where the delta plus. Just look at the distance here between the delta plus and the O minus in each instance.
Oh,
The-
okay.
The one that's closest is going to be the one that's more stabilizing.
Okay. Thank you.
Okay. Any other questions?
Does the delta minus on the fluorine not play any kind of
No.
repulsion role
No.
in that?
No, because it's really more a case of the electrons in the bonds here sort of being more attracted to the delta plus. It's like think of it like a wire, and you know the electrons are sort of all attracted over here. It's almost like the delta plus is kind of pulling the negative charge off the oxygen. It doesn't really do that, but I'm saying that's how it feels. And the
So that would bring the oxygen group there closer to the rest of the molecule and make it more.
I don't know if I'd say that. I'm just saying the negative charge on the oxygen sort of moves closer to the delta plus.
Okay.
You can look at it that way. It's called an inductive effect because it's through bonds, but it's not a through space effect. So the delta minus here doesn't have anything to do with it. All right. Any other questions?
So what if the fluorine was like a different atom that was less electronegative than carbon and it had the partial positive charge on it? Would that make a difference at which one was more stable?
It sure would, but we're not dealing with that scenario right now. You've got to cool your jets here, Sierra. While
Am I ahead of you?
Yeah, I'll get there. I'll get there.
Okay.
You're stealing my thunder.
I'm sorry. Thank you.
All right, let's back at this one here. So the situation is that the delta plus is closer to the O minus, which makes the A minus more stable. So you look at the answer here and you see the A minus is more stable because the delta plus is closer to the O minus, which leads to greater stabilization of the anion. You cannot write a good answer for anion stability without talking about the delta pluses. Now, a lot of people don't like talking about them. It's almost like delta pluses are against their religion or something, so they just don't want to say anything about it. What they'd rather say is F is closer, that makes it more stable. Well, that's not enough for me. It's almost like, I don't know if anybody's really familiar with Seinfeld, but there was this episode about yada yada. Anyway, you can look it up on YouTube. But somebody was yada yadaing out the best part. And the best part of this is the delta plus. And I don't want people yada yadaing out the delta plus. So what I sometimes hear people say is, oh, F is closer, yada yada, that makes it more stable. But we're not going to be yada yadaing here. All right. Anybody got any questions?
Yes, I always get this confused. So how do we know where the delta plus and the delta minus go? Is it always just going to go on the element?
Well, the delta minus will always go on the non-carbon element for one thing, and the delta plus goes on the carbon connected to that element.
Okay.
Always. Because we're always talking about bond polarity here, just individual bond polarity.
What about in situations where the element it's bonded to is less polar, such as like boron?
It's never going to happen. We're only going to be dealing with carbon compounds. Everything's going to be more electronegative than that carbon.
We're not dealing with boron at all?
Nope.
Okay.
Because it's boron. That wasn't a very good joke. But anyway, does anybody have any questions?
Dr. Musgrave, in
Yes,
the last
Courtney.
example, how would you do it on that? Or is that one the exception to it when you just talk about electronegativity?
Could you repeat that, please, Courtney?
Okay, so the last one you did, like the last slide with the difference in
Yes,
electronegativity,
that's right, yes.
you not have to put it for that?
No, because the difference here between this one and the previous one is that here the negative charge is on a completely different atom, Courtney. Do you see that? It's on N here and on C here.
Yeah.
And in this one, they're both on the O negative, and now we're looking at something different in order to determine which anion is more stable.
Okay.
Is that all right? I'm glad you brought that up, but that's not the last time I'll be bringing that up either, because that is important.
When you say it's on the N and it's on the C, like, I don't understand. How are you determining that? The negative, I mean.
Well, I mean, when you take the H off, the negative charge is left on the N. When you take this H off, it's left on the C. You're overthinking it, Keisha.
As usual.
Is that all right?
Yes.
Okay.
So basically we do the partial charges for ones that are isomers.
Isomers? No, I can't say that. But what I can say is you'll definitely do it when the negative charge is on the same atom.
Okay.
All right, and I will make a big deal of that later. All right, so the second scenario, number two. Ooh, did it again. I hate this thing. I wish I had a better drawing program. This one is awful. I like the one I have on my Mac. This one I'm not so fond of. All right, this one is about distance. And yeah, it's worth pointing out that it's the same element attached here, the Y, it's just in a different place. So delta plus, delta minus, delta plus, delta minus. So delta plus closer to X minus. And that means that that one is going to be the more stable of the two anions. Does anybody have any questions? All right, let's look at the next one. So Sierra, this is what you were asking about. What happens if it's a different atom? But. Look where they're attached. They're attached to the same place. Right, that's the difference. Hopefully you're clear on that. Is everybody okay?
So you're never going to get it to where they're attached on like different spots and they're different atoms?
Oh, come on, that's a bit cruel, isn't it?
It would be cruel, but
what do you think I am? Huh?
Orgochem can be cruel sometimes. I don't think it's you. It's just the curriculum in general.
No, I will tell you this. Anything you get will be unambiguous. Right? I mean, it's going to be obvious.
Thank you.
All right.
I appreciate it.
When you say it is attached, what is it? Is that the delta plus and minus?
Yeah, oh, the F and the BR. That's what I'm talking about. So we've got these electronegative elements. They're more electronegative than C in both cases, obviously. But they're both attached to the same C, same location on the different molecules. Now, the thing I would say about this one is if you look at CF and you look at CBr, the bond is actually longer in the BR because the BR is bigger. But what happens here is that we have a big delta minus here, which means we have a big delta plus, and down here we have a little delta.
Yeah, I was about to say that. The bigger the delta minus, then the delta plus must be just as big, but in the opposite electrical charge.
That's right. But you destroyed my little demonstration by talking over me when I was being quiet by saying little delta minus, little delta plus.
My sincerest apologies.
It's okay. It's okay. But the point is that the bigger the delta plus, that means that it's going to be stabilizing the O minus more. So the CF will stabilize the O minus better than the CBr will, just because the delta minus is going to be bigger, which makes the delta plus bigger. Does anybody have any questions about that? All right, let's take a look at that. That's going to be scenario 3. And scenario 3, again, we have the negative charge on the same atom. And you can see here that we've got, again, X minus, but we'll have a different Z here. So if Y more electronegative than Z, and that would mean that, again, this is the more stable of those two anions. Any questions? Scenario 4. You can see the difference there. We've got one F on one, two Fs on the other. No, that's the way we see it. One F on one, two Fs on the other. This is how I explain it. If you've got a situation where you've got, say, two Fs attached to a C, it's almost like you've got delta minus, and this C would be 2 times delta plus versus this situation where we only have one F, and that means we've got delta minus and delta plus. So again, we've got a bigger delta plus because we've got more Fs attached to the atom. Does anybody have any questions about this one? So it's the same atom. Again, I'm not going to give you more of one. I'm not going to give you an F and then something with 2 BRs on it. You know, it's crazy. But I will give, say, 1 F, 2 Fs, 3 Fs. You know, that's a different thing.
Wait, so can you repeat that reasoning one more time? I'm sorry.
So if you got the Fs there, if you got 2 Fs, it doubles the delta plus charge on the C.
Gotcha. Thank you.
All right. Does anybody else have any questions? All right. That's scenario 4. I'll erase that. Remember, when you go back and do this, you'll see me erase stuff. So I've got to. I need to kind of keep my real estate clean here. Damn.
On the one before this, it was the fluorine that was more electronegative, correct?
That's right. There was 2 different atoms, Y and Z, fluorine and bromine, fluorine, chlorine, or something like that. That's an example. But notice they're attached to the same location as well. Okay. Actually, I shouldn't use F. I should use, I'll use Y. Sorry. Just because it doesn't have to be F. Could be chlorine, bromine, or something else. So more Ys, bigger delta plus. Now, if delta plus is on this C that I've put the arrow on here. Okay. So more Ys, bigger delta plus. On C. And that would mean, again, this one was the more stable of the 2 anions. All right, does anybody have any questions? Any questions? All right, I'm going to leave those 4 scenarios there because we're going to be looking at some examples here. And I'll show you some examples from this problems test 1, which is the blue book, or if you printed this out, one of the 2. All right, let's take a look. All right, here we go. So what I want you to be able to do is look at each of these examples and be able to tell, and I'm not going to do all of them, but be able to tell which scenario is in play here in each case. All right, so I'll drag this over here and we'll look at it that way. Okay, so which scenario are we looking at for question 1? 1, 2, 3, or 4?
1.
It's 1 because when we take the H off here, we'll be left with O negative. If we take this H here off, and you only take off one H, it'll be NH negative. I do have the answers down here as well, and you can see this. This is what it becomes. So the OH becomes O negative plus H plus. The NH2 becomes NH negative and H plus. But in each case, you've got the negative charge on different atoms. So the O negative and negative. All right, anybody got any questions? All right, look at number 3. Which scenario do you think is going to be the one at play there? For number 3. So what's that? Sorry?
Was it 2?
It's 2, yeah. It's about the distance. Because if you look at the, again, if you look at the negative charges, they're on the same atom now. They're on both on oxygen. But the delta plus is going to be in a different location. And that's going to be determined by where the F is on the chain. So the delta plus is actually on the C here. It's on this C here. It's hard to see it in the diagram, but that's where it is. It's drawn on the C. Okay, any questions? Okay, let's look at number 4. What scenario do you think that would be?
Number 1.
Yeah, it's number 1 again because you'll have CH 2 minus and O minus. So the negative charge will be on separate atoms. So don't worry about the F's there. Where are we? Here we go. The F's don't affect anything because they both have the same number of F's in the same locations. So it's not any of the other scenarios. The multiple F's don't make a difference here. But we do have negative on the C and negative on the O. Does anybody have any questions? Okay.
Yeah. Professor, when we answer our questions during the test, do we do what you did, like we draw the diagrams as we answer?
You do. You do.
Okay.
I'm going to show you some test questions in a minute, okay, Nora?
Okay, thank you.
All right, there is another one here, another worksheet here somewhere, a little bit further on. Okay, I think I might put it in.
But I have a question about the ones you were just showing us.
Okay, yeah.
Go back to it.
All right, I'm going back. Is that you, Rebecca?
No, it's Julie.
Oh, it's Julie. Okay, what's up?
On the ones that you skipped, which
Yeah.
were 2 and 5. Okay. Now 2 is sort of halfway between number 3 and number 4, I guess.
Yeah, I can see him. Yeah.
But number 5, would you cancel out things like this?
No, see, in this case, it's more like scenario. Both 2 and 5 are examples of scenario 3, because Cl is more electronegative than H in the same position.
Okay.
Same with the Fs here. They're more electronegative than the H's that are attached to these Cs.
How do we know there's H's attached to the C's?
Because they're line structures, and we assume that there's the right number of hydrogens. Remember we talked about this on the first day.
On every compound?
Yes.
There's always hydrogens?
Well, when in these line structures, yeah.
Okay.
So those wouldn't be examples of 4?
No, no, I wouldn't say so. It's really Y and Z, where Y is in the number 2, it's Cl, and Z is H. I think it's more like scenario 3.
Oh, okay.
In my opinion.
Okay.
I don't know. You could argue it's 4 and say, well, this one has 2 and the other one has none. I suppose. If you made a case for 4, I'd have to listen to it.
Okay, thanks.
All right. Anybody got any other questions before I show you the other set? All right. I'm going now. Nobody's going to stop me. Okay, the other set I think I put at the end. Here we go. All right, another 7 examples. Not there. Let's look at number 2. Which scenario do you think number 2? This is number 2 here that I'm circling with my cursor.
2.
2, because the F is in different locations. It's closer here on this one than it is on this one. What about number 3? What scenario are we talking about there?
4.
4, because this one has 2 Fs. This has one F in the same position. What about number 4? What scenario are we looking at there?
3.
3, because we got Br and F, but they're on the same carbon. Okay, what about number 5? Which scenario are we looking at there? Oh, it's a tougher one.
Is that also 3?
It's also 3. It's not 1 because they're both going to end up having the negative on the C here, and one has to have the negative on different atoms. So it's definitely not 1. It would be 3 because you've got the same number of Fs and same number of Cls. What about number 6? Which scenario is that one?
2.
Yep, because the 2 Fs here are closer than the 2 Fs here. And number 7, which scenario would that be?
3.
That's 3, yeah. And again, you know, it can't be 1 because that'll be NH minus. That'll be NH minus. It's only 1 when the negative charge appears on a different atom. I'll say that again. It's only 1 when the negative charge appears on a different atom. So the other thing that I would say is you'll notice that in these instances, and I will show this on number 3 as well, scenarios 2, 3, and 4 do require the explanations have something to do with the delta plus. And you can't yada yada out the delta plus. So for number 2, you can't say the Y is closer to the X minus. That makes it more stable. No, the Y has the delta plus that is going to be closer. That's what stabilizes it. 3, the delta plus is bigger on 1 than it is the other. And in 4, the delta plus is bigger as well because of the greater number.
If you said like more electronegative instead of doing the delta pluses, would that be correct as well?
Not really.
Okay.
I wouldn't. Well, you know, I mean, in the case of 3, yeah, because Y is more electronegative than Z, but you'd also have to say then that gives it a bigger delta plus. You have to have something in there about the delta plus.
So if you draw the delta pluses on your diagram as you answer, does that explain enough, or do you have to write out why you drew the delta pluses as well?
Well, you have to give some context to the delta pluses then, explaining why one might be bigger than the other or why it might mean more than the other. You see, in the case of scenario 2, it's because one delta plus is closer, right? But in the case of scenario 3 and 4, it's because the delta pluses are bigger.
Okay, and then the more of the same element we have, like let's say we have 3 fluorines, that means it's the bigger delta?
Yes, bigger delta.
And
plus, yeah.
that's why it's okay.
Yeah. So you'll notice the key word with number 2 is closer, right? With 3 and 4, it's about the delta plus being bigger. All right. Anybody got any other questions? Okay. All right. Let me go back here. Let's take a look at some test questions. And I'll just I'll just pull up the keys here. Alternate. There we go. I'll just pull up the keys. So fall 2016. Oh, we're in the wrong. Sorry. We're in the wrong test here. We're not looking at that stuff yet. That's scary. Let's try it again. Okay, so this is question number 2 on the test. All right. So which of the following compounds is more acidic and why? Draw equations showing dissociation. So you show the dissociation. And in this instance, you can see the student did the delta plus and delta minus. They didn't have to. Why? Because the negative charge is going to be on a separate atom. So if the O being more electronegative than the N is a good enough explanation for why the anion for the first one is more stable than the anion for the second one. So the O minus anion is more stable than the N minus anion, just because O is more electronegative than N. The other thing I'll point out here is that often I'll see this kind of answer, O minus is more electronegative than N minus. Well, that's not really true. O is more electronegative than N. The O minus and N minus doesn't necessarily follow. But I don't know why they're doing it. I get it, but it's wrong. You'll notice here that there is a statement that links anion stability to acidity. And then we can say that one compound here, because that's what we're asking, is which one of these is more acidic. We say this one's more acidic because its anion is more stable. In a nutshell, that's the reason. This one's more acidic because its anion, which is this, is more stable. Does anybody have any questions?
Yeah, Dr.
Yeah.
Musk. For that test, the student did the line structures for each one, but in Gen Chem, remember how you had us like give them names like AH and A minus and BH and B minus?
Oh, you can do that if you want.
Okay, perfect.
Yeah, that's right. You can assign. You'll see that in some of the other examples I'll show you in a second. But a student could label this AH and A minus, BH and B minus, and then not have to rewrite them down here. As long as you know which ones you're talking about at the time. Thanks, Courtney. That's true. Yeah. All right. Yeah. I did this in I think it was Chem 2, actually. Oh, test 1. Let's go back. We'll take a look at another one. Where are we? Here we go. Okay, so for this one, you can see the scenario here. This one has more F's on it than this one does. So, back to my diagram here, it's scenario 4. You'll notice that we take the H off the S here. The S becomes S negative, and it's going to be the same atom that's carrying the negative charge here. So looking at it, we got the delta minus, delta pluses. Those did have to be put on. So more F creates more delta minus, which gives more delta plus on the C, which creates a more stable anion. That's fine. Now down here, I don't think the student, you see I circled these things. They didn't put the delta pluses in. That's why they didn't get full credit here. And then they have this statement here about the one anion being more stable than the other. That was fine. But they talked about the delta plus and the delta minus, but they didn't mark them on the actual diagrams themselves. So anything I've circled here is stuff I added. All right, any questions? Okay. go take a look at this next one here. I don't know if there's any. Hopefully there will be. Just see. Yeah, you can see how student label is AH and BH, and then they talked about them up here, and that's cool. So this one would be scenario 3 with the different elements here, and you can see again the delta minus and delta minus, delta plus here, delta plus, delta minus, delta minus. B minus is more stable than A minus because fluorine is more electronegative and therefore gives a bigger delta plus. BH is more acidic than AH. So that's okay. That works as well because the statement has been made here about the anion stability as well. So they've kind of incorporated that into the answer. All right, does anybody have any questions about that one? Okay, last one. So for this one here, again, it's scenario 3, just like it was before. Same deal. And you'll notice again, the students put the delta pluses on. Said that this one is more stable, the one with the F on it is more stable than the one with the CL. So that makes that anion more stable, which makes the compound it came from, which is one with the F here, more acidic. Okay, so there you go. I mean, it gives you an idea of what we're going to see. I'd recommend doing the problems in the blue book that I went through, doing them again, and writing them out, writing out the full answers. I mean, the full answers are there in the blue book too, exactly what's expected. You can just follow along with that. All right, does anybody have any other questions? All right, let's go back here. All right, now I need to. There we go.
Dr. Mercer?
Yeah.
Quick question. Just out of curiosity, when should the first test be? Do you know?
I can't remember. It's in the syllabus.
Okay.
I'm looking at it. It says September 7th.
Thank you.
Yeah, it seems reasonable.
It's the Wednesday of that week, so it's actually the 9th, by the way.
It's actually the 9th. Yeah, there you go. Labor Day is the 7th. So
the week of the 7th. I'm sorry.
Yeah, that's all right. So test 1 is on September 9th. All right. Everybody clear on that?
Stereochemistry, what does that entail?
I'm not going to talk about it. It's got nothing to do with stereos, though. I can tell you that.
All right, thanks. I was worried about that. Yeah.
No, we'll worry about that more when we get to test 2. I promise. You'll get more stereochemistry than you ever wanted in your entire life.
That bad, huh?
Yeah. Well. All right.
Fun.
Yeah. All right. Well, anyway. So just a little bit of a thing here about how to figure out what charge something has, depending on how many bonds it has. So I mentioned, or I've made a big deal of the fact when carbon likes to have 4 bonds, nitrogen likes to have 3, oxygen likes to have 2, fluorine likes to have 1. But when they carry different numbers of bonds, they also carry different charges. I'm not going to go into why. You can look at this in my videos, but with nitrogen, you can see that when it has more bonds than what it's supposed to have, 4, that it's positive, and then when it has fewer bonds, 2, it's negative. Same with oxygen, 3 bonds plus, 1 bond negative, and fluorine, if it had 2 bonds, it'd be positive. Now carbon's kind of funny, it can be plus or minus, depending on if it's got an electron pair on it or not, but I don't really want to go into that either. Again, it's just something that's a little bit helpful, a helpful observation, we'll say. I've got some examples of that here in the next slide. This is the PowerPoint slide from hell because it's got so much information on it. I don't usually do this, but I have here. So resonant structures. Resonance is about stabilization by moving electrons around. But you're only moving electrons and bonds, not atoms. That's what a resonant structure does. And it's not an equilibrium situation either. These things are not affected by changes in temperature or pH or anything else, but just straight movement of charges and bonds. And the application we're going to have for resonant structures is showing how resonance can stabilize a negative charge. If it can stabilize a negative charge, it means it can make a more stable anion, which means that we can talk about it in terms of acidity as well, and how that might affect stability of anions. All right, so let's go take a look at some examples of resonance. The first one is one of the more popular examples of resonance. It's called benzene, and it's a compound that has 3 double bonds that are alternating. So it goes double, single, double, single, double, single, double, single, all the way around, 6-membered ring. And you'll notice that technically those double bonds could be drawn in 1 or 2 locations to keep that pattern. So this one or this one, these are called resonant structures. In reality though, neither of these actually exists. It's something in between. So when we look at benzene, we know, as we talked about last week, or yeah, it was last Monday actually, I talked about how double bonds are shorter than single bonds, right, because of the hybridization. sp2 is shorter than sp3. So you might expect in a compound like this that these bonds would be shorter, the double bonds would be shorter than the single bonds. Actually, it turns out all the bond lengths in benzene are the same, but they're about halfway in between a single and double bond, which lends credence to the fact that what's going on is the electrons are being what's called delocalized. They're not in the same place. They're being moved all around the place. So that's an example of resonance right there. Now, a couple of other examples, and the one we're going to focus on here is this pattern here, where we've got a negative charge, but it's very specific though. It's very specific. We have a negative charge on an element that's single bonded to another element that's double or triple bonded to an element next to it, like this. So it's X, single bond Y, double bond Z. It's specifically that with the negative charge on the X. And what can happen is that if you have specifically this pattern, then that negative charge can move and end up on the Z. But you'll notice what happens is now we've got a double bond between the X and the Y. I've got this double-headed arrow here that represents it being a resonant structure that shows that movement of the bond and the electron. So an example of that would be this situation here, where you've got a negative on the O, and we can move the electrons into the CO bond, and then we can move electrons from the C double bond O onto the O, and then we've got the negative, the net effect is the negative has moved from one O to the other. But we know that in reality, the negative is really spread equally between these 2 oxygen atoms, just like up here in the benzene ring. All right, so let's take a look at what I'm talking about here. I'll draw a couple of diagrams. So let's look at this pattern that I'm talking about here. And this is really, I think it's your first exposure to these arrows that I'm talking about. These arrows here are very important to us. They show electron movement. So look at the story I'm trying to tell with that arrow. It's a wonderful story. It's a story of a negative charge that's on an X atom that is going to be pushed in between the X and Y atoms to form a double bond, because by putting that negative charge in there, we're effectively putting in 2 extra electrons. And now that Y has too many bonds on it, so this bond has to break and the electrons have to go on the Z. So the net effect of that is going to be this. The X double bonded to the Y, single bonded to the Z minus. And the X negative, the negative from the X has now moved on to the Z.
Would this by any chance be similar to an electric current?
Not really. A little bit. I suppose, a little bit.
So what's the purpose of moving the electrons around if it's just going to move back and forth between the two?
The point is that if they can move back and forth between the two, then the negative charge can spread out between the X and the Z. If that can't happen, then the negative charge is stuck.
Okay, so will it keep moving between the two states, or once it moves, like, will it keep going back and forth between the two until it bonds to something else?
No. What will happen is it moves so quickly that you can't see that it's really just split between the two. The situation looks like this up here, Sierra, with the half negative charge on the X and half a negative charge on the Z.
Why is it 2 electrons though?
Because if you look at the X, if it's X negative, it looks like this. And what we're doing is taking 2 of those electrons off.
I don't understand. I thought what would make it negative would having an extra electron.
Well, that's the thing. One of those electrons that I've got the arrow on was the electron that's actually producing that negative charge, Julie. But you don't have to be aware of that because it's there. You know the negative charge is there, so you know the extra electron's there. But it's inferred, if you will.
So there's not really 6 there, there's 7?
Well, if it was neutral, there'd be 7, yeah.
I don't understand.
Well, it doesn't matter. I'm not sorry. It doesn't. I'm not saying it doesn't matter if you don't understand. I'm saying it doesn't matter. You don't have to understand that. All you have to understand is that this arrow is showing the movement of 2 electrons.
Okay.
And that negative charge is due to the fact that the X has 1 electron more than it needs to have to make it neutral. In a way, you can look at it this way. All right, you could say, let's say X was O. That means that it has a certain number of electrons because it has a certain number of protons. It's got 8 electrons, 8 protons in total. But in order to make sure the electrons are paired here, it can gain an extra electron, which would make it negatively charged.
So what determines if you can move the charges around and everything? Like, how do you know what kinds of molecules can do that?
They have to have this pattern. X negative, single bond, Y, double bond Z, where X and Y and Z can be any element. But it has to be that pattern. Let me show you some examples of things that don't resonate, okay?
Okay.
So this situation here, where you've got the negative charge, and then there's a single bond and another single bond, that's not going to resonate. It's not going to be resonant. There's no resonance there. The negative charge would need to be on this atom here where I'm pointing, if you can see.
Mm-hmm.
Not on the end. If it's here, it can't move. This O negative can't move either because there's no double bond to interact with.
Uh-huh.
And this one here, the negative charge is on the double bond, so that one is not subject to resonance either.
Oh, okay. It would have to be on the carbon on the end
This
to
one
resonate.
here, that's exactly right. That's exactly right. Now this one here, we're actually moving atoms around, so that's not going to be good either. That's an equilibrium situation. So none of these are resonance situations.
Because atoms don't move, just their bonds and their...
bonds and charges, that's it. Bonds and charges. So just to, as a matter of application then, let's say you've got 2 compounds. You've got this one here and this one here. This one with double bond O in the OH, and one here that just has an OH on it. So what we do is we split this up into the anion and H+, just like we were doing. Now you can see that one anion is going to be more stable than the other. So the one with which we can actually apply resonance, that's the one that's going to be more stable. whereas the other one, which doesn't have resonance, will not be more stable, or won't be stable at all, because the negative charge is basically stuck on the oxygen. But in the case of the one that has resonance, the negative charge is split pretty evenly between this oxygen at the top and this oxygen at the bottom.
So to be able to do that type of resonance, it has to be the same atom? Like it can't be like an oxygen and then like the double bond to something different?
It could.
Okay.
But if it was, it wouldn't actually be half and half. It would be like, it would depend on the electronegativity. So the one that was more electronegative would carry a greater share of the negative charge, but it would still be split between the two.
So like, so like 2/3 and 1/3 instead of half and half.
Yeah, that could happen. That could happen if they're different atoms. But if it's the same atom, it's just going to be half and half.
And the half and half is because the electron moves, or sorry, the electrons move so fast that
you just don't
practically it's half a charge at any given time.
Yep, dead right. Yeah, neither of these structures actually truly exists, but we do write them in order to be able to show the extremes so we can get an idea of what's in the middle. You know, it's like everything, the truth always lies somewhere in between. All right. Okay, any other questions?
Can we see some, like, you're going to show us examples, right? Like on the tests and stuff for these?
Of course, Sierra. Do you think I was just going to move on?
No, I figured not, but I thought I'd ask.
You thought you'd ask. Hey, you know, you would have been on me if I didn't, right? I thought
Well, yeah, you look confused.
Yeah, I thought I was almost going to make a joke and say, yeah, I'll just move on to the next part here, and then
next two topics.
Yeah, it wouldn't have been very funny. All right, let's take a squiz. This is the kind of question you'll be asked. All right, there you go. So we've got these two compounds here. And the question is, which one is more stable? Which anion is more stable? Draw resonance diagrams showing electron movement where appropriate. So it should be easy enough for you to look at this and be able to determine which one of these follows this pattern that I have over here. And I'm hoping you can see that the one that's circled is the one that will follow this pattern, and this one over here will not follow that pattern. Is anybody confused by that? The pattern I'm talking about is specifically this one. A negatively charged element single bonded to another element that's double bonded to another element. You can see that that's what we've got over here. Is everybody okay with that?
Mm-hmm.
Now, hang on. Yeah?
Sorry, the other compound, it's because it's single bonded and then it's single bonded and then it's double bonded. That's why it's wrong, right? Okay, just to make sure. Thank you.
That's right. Yes, I like to hear that. That's really good. All right, now it's asking to show the electron movement, right? Now that's the fun part here. So let's see how that's done. So we've got our diagram here. And then we draw it, we follow the same pattern as we've got up here. So the negative charge goes into the bond, and then these electrons come from that bond and go onto that atom. So as you can see, I'm doing exactly the same thing here as I did in the pattern. So the arrow comes from, it's either the negative charge or the atom. It doesn't really matter which, but the arrow is going into the bond. It's going into that space between the two to form the double bond. And then this double bond, the arrow comes from the bond, because that's where the electrons are, and goes on to the Z. So when we draw the second structure, we're just, again, following the pattern. And that's the end result. So now we've got a double bond between the O and the C. That's the story that arrow is telling. And then the story of the other arrow is that the electrons moved out of the double bond and onto that specific atom. you'll notice the arrow points to the atom specifically, because that's the story we're trying to tell. And again, the net result is that the negative has moved from the O to the C.
So basically just like do it backwards.
Well,
like rewrite it backwards.
You could say that, but I'd really prefer that you know what's happening in the context of the arrows. The arrows are telling a story, and I want you to understand that story. It's a beautiful story. It's a story of moving on from one atom to another.
You should write breakup cards.
Ah, dear. All right. Any questions? You ain't seen nothing yet. Once we get to the whole SN1, SN2 thing, it becomes even better than that. Look forward to it. All right. So that's what we're looking for here in this one. And you can see that that's what the student's done.
So how would you word the answer? Because you want like a pair, well, sentences written.
No, actually, not really. I mean, this is you need to circle which one is which anion is more stable, and then you just draw the resonance diagrams. Sometimes you can add some stuff here, but that's really not necessary.
Okay, perfect.
This is what I'm looking for. This business here, where we're actually showing the resonance, showing one structure and what it leads to.
Gotcha. So you wouldn't have to even attempt to do the other one like they did in the example?
No.
Has no resonance?
No, that's just overkill.
You just want us to draw the story, not to tell the story.
Yeah, that's right. In this case, I didn't ask you to tell the story. Did I ask anybody to tell any stories here? I think I've already read, draw resonance diagram showing electron movement where appropriate. It ain't appropriate here, but it's definitely appropriate here. All right, any other questions? So this is part of the same question over here. Which of these compounds is more acidic and why? So it's kind of related to question 2. So you'll notice that the compounds I give you are exactly the same compounds. I'll say it again, they're exactly the same compounds, except now they have H's where the negatives are. All right, see, they're the same thing. Yeah? All right. So you've got to be thinking, well, what's up here in the first part of number 3? It better have something to do with what's down here at the second part of number 3. Wouldn't you agree?
Yes.
Yes.
Yes, right. So what we can do is we can say, well, since the anion from this first one here, which is the top one, the one that's subject to resonance, since this anion is more stable than this anion, it makes this compound here, the one that leads to the resonance stabilized anion, more acidic. And that's it in a nutshell.
Okay, so because it has resonance, it's more stable, and since it's more stable, it's more acidic.
So since the anion's more stable, the original compound's more acidic, to be super clear about that.
Okay.
All right, is that okay? So it's always, the compound's more acidic because its anion is more stable. I'll say it again. The compound is more acidic because the negatively charged species is more stable. And, that's really important to me. All right, any other questions? All right, I'm going to leave it to you to look through the other examples of these and look for the patterns. And remember, we will be doing a review day, and that'll be probably about a week and a half, 2 weeks or so, something like that. And that's when you can ask other questions about these, and we'll go through more examples of these on the review day if necessary. In the meantime, though, I want you to look through some of those other examples. There's also some examples of these in the blue book, and I'm just going to point those out to you. And those are on page, here we go. These are on page, whatever that is, page 13. Yes, at page 13. I go through resonance structures there as well, examples of resonance structures. All right, so that's another resource for you to look at. Plus you've got the videos as well. All right. Well, I've only got 5 minutes to look at functional groups, but that's about all I need. And again, I can put it on you to read a little bit more about the functional groups. Now, I'm actually very kind with functional groups, a lot kinder than I used to be. Oh, I've got the isomers as well. There's no way I'm going to cover all this today. You know what? I'm going to leave it. I'm going to leave it at that today. I'm going to have to start covering the, you know, this is the first time I've done it like this, so my timing is not up to par here by the looks of things. It looks like I had to spend less. Well, I had to move this to the next class is what I had to do. No, I'm not going to rush it.
Thank you.
So we will do we'll do isomers and we'll do functional groups on Monday. All right.
Thank you.
Thank you.
All right, and I'll see you all later. I'll see some of you in lab, but if anybody wants to hang around and ask questions, they can. For the rest of you, bye.
Ciao.
Bye.
Anybody have questions?
Can I ask questions about lab or just lecture?
We'll just lecture right now, but Mariah, I'll start. You know, when I start the lab, you can ask questions about lab.
Okay, I'll come back for lab. Thank you.
All right, thanks, Mariah. Anybody else have any questions?
Musgrave, to stay
Courtney.
like up to date, like studying, because you know how like my classes are this semester. Like I've been trying to like start studying earlier. Should we just be doing like the tests and the practice tests and like reviewing PowerPoint and doing everything?
And looking at the similar questions that I'm pointing out in the blue book as we go, because those are good exercises to do to make sure you understand what's going on.
Okay, can I possibly like fill out like fall 2016, how like, remember how after class I used to ask you if it was okay, like the way I put my answers?
Oh, sure. But understand that I also have the keys there as well. So you can compare it to the keys that are there, but you are more than welcome to send me what you have and I'll tell you if it's okay. All right, any other questions? Ryan, no. Yep, Ryan, do you have any questions, Ryan? All right. Okay, we'll end it here.